Belkin joining us to give the IDSS Distinguished Lecture Series today. So Misha is a professor at UCS. It's manifold learning and more recently the theoretical foundations for deep learning. So please join me in welcoming him. Thanks for coming.
Thank you very much. Thank you, and yeah, it's very nice to be here. This is the first time I'm actually giving like post-COVID physical talk. So that's.
Sorry, could you just double check the mic as well?
Oh, the mic. Yes.
How post-COVID?
Yeah. So. If something is wrong, you know, I have a good excuse. So what I would like to talk about today is really a couple of things which relate to optimization, transition to linearity, and one very interesting deviation from linearity. Specifically for neural network, but optimization framework is actually kind of more general for over-parameterized systems. And this work, almost all of it is joined with my students Xiaowei Liu and Li Binzhu, and parts of it are with Li Kehui and Ajit Radhakrishnan, who is here. What is this talk? So first, I will talk about optimization over parameterized systems. And the kind of interesting point about that is that it seems that over parameterized systems sort of generically behave as if they were linear with respect to optimization, although, of course, they are nonlinear. But somehow you can think of it as if they're linear, and you know, it's a reasonable way to think about it, which in the sense that I will describe it. Now, the other thing, the second part of the talk, is this transition to linearity, which is, relates to this recently sort of found phenomenon of constant NTK, which is the fact that for quite general wide neural network with linear output layers, they actually implement linear functions in some sort of strictly defined sense. And that was kind of surprising because, you know, why should they be linear? And I'll sort of give an argument, but I think it's a very interesting thing on its own. And finally, I will talk about this recently discovered Catapult Dynamics, and which we don't have a great theory of, but I'll point out some limited theory, but I'll point out some very interesting sort of deviation from nonlinearity. And this deviation actually is particularly interesting because it seems that it's somehow discontinuous limit deviation. I'll like non-perturbative deviation, which I'll say what it is. Okay, so let's, and this is based on like several recent papers. In particular, I wrote, parts of it are based on parts of what I will discuss today. I wrote this kind of review position paper, which sort of summarizes some of my sort of thinking about various properties of deep learning through the prism of interpolation, as somehow can be understood from the interpolation point of view. Okay, so let's start. And so as we know, models in deep learning, right, we have for deep learning or machine learning, right, we have models. And we basically almost always use some sort of empirical, algorithmic empirical risk minimization, right? So you have some loss function, you have xi, yi, and you're trying to minimize some loss by gradient descent, stochastic gradient descent, some variation of those things. Almost always first order methods. Now, the key question had been like, why is SGD so successful in optimizing this highly nonlinear network? And that's maybe the first thing I will discuss. And it turns out that you can actually understand this. I think now we sort of understand the answer to this, at least to a reasonable degree of granularity. And sort of traditional view has been that tractable optimization is equal to local convexity. And sort of my first point would be to discuss Polyak-Lyasevich condition as a substitute for convexity, which can be satisfied by these neural networks. And so first, let's think about sort of learning and solving a system of equations. And the basic setting is, well, if I want to fit data, I essentially want to find W, right, such that f of xi is equal to yi. Of course, not necessarily exactly, but maybe approximately. And if you aggregate f of w into f of for each I, right, if you aggregate it into one map, this is simply saying that we want to solve the system of equations f of w equals y, where w is a vector of my parameter. So it's a map from Rm to Rn, when n is the number of data points. Now, equivalently, this is minimizing the square loss, right? F of w minus y equals to squared. So you can kind of think about a lot of machine learning as simply minimizing the square loss. It's not very far from actually what happens. And one thing it's a little bit of an aside, but I would like to point this out. Let me just point out that square loss is OK to use for classification, and this is based on recent work that Li Kehui and I did. We actually took a bunch of different architectures. This is specifically for NLP problems, but we did the same thing for speech and for vision. And what you can see that if you use square loss instead of cross entropy for classification, you actually get better results. OK, it's not hugely better, so it's not by maybe 0.5% or something. But at the very least, there is this kind of conception that you are supposed to use cross entropy for classification and square loss for regression. It's not really true. You can use square loss for classification. And in fact, we did 20 different experiments. And in 17 of them, square loss was as good or better. So at the very least, it's very, very comparable. So classification or regression, you can always use square loss. And in fact, it even had smaller variance with respect to initialization. OK, so that's an aside. But that's maybe to justify a little bit why square loss is a reasonable thing to use, even when we talk about classification problems. Now, sort of, what is the basic kind of, so the first intuition here? The first intuition is like sort of classical landscape. If we think about non-convexity, right, we think about something like that. If we have some crazy landscape like this, of course, there is no hope to find a global minimum, right? Because a global minimum here is not really different from any of the local minima, right? With any gradient descent type method, the best you can do is to find one of those, or maybe several. But how do you know which one of them is global? And there is really not much hope. And therefore, I think that's kind of maybe psychologically why this has been considered intractable. And then, of course, neural network came, and people would say, oh, yeah, we just take a big neural network and we just optimize it, and it works. And from this point of view, it's very surprising. But that's maybe not the right picture to look at. And the right picture is something like this. And what's the difference between these two? Because this is an overparameterized system. So you can see that there are the number of parameters here. So in some sense, if you have an underparameterized system, the landscape looks something like this. If you have an overparameterized system, it looks like that. Because when the number of parameters, so if m is bigger than n, you expect to have many solutions. You expect to have a manifold of solutions, to be precise. And you have these valleys of global minima. And it's maybe not crazy just from looking at this to think that if you drop a ball here, right, it will roll down to the valley. So gradient descent will converge to a global minimum. So this is kind of maybe the first sort of order intuition about this. Now, interestingly enough, it's really very easy to prove that such landscapes are essentially never convex. And what do I mean by this? Well, whenever you have a manifold of global minima, that's a set of minimizers of if my loss function is convex, then the set of minimizers of a convex function has to be a convex set. And the only way this curve can be convex if it's a straight line. So if there is any curvature in this manifold, it cannot be convex. That's it. And of course, if you have an arbitrary system, you wouldn't expect that there is no curvature. That's a very special condition for it to be affine. So why would it be affine? So essentially, the things are never convex. So it's a very strong condition for them to be convex. So if it's not convex, then what? So not only that, but convexity actually has a basic underlying problem, right? And okay, it's kind of obvious, but if you change the coordinate system in a convex, if you have a convex transformation and you have a convex, so imagine that this is just function of one variable to make simple. Suppose even both of them are convex, then phi prime prime is positive, this thing is positive. But the second derivative of the product has this extra term, and phi prime doesn't have to be positive even for a convex function. So there is no guarantee that this thing is convex. So you cannot guarantee any convexity for a composition. And of course, we like to have composition in machine learning because this is some sort of feature change, transformation. So convexity is somehow seems very fragile notion, not really. Not nice, and we will see. It's for over-parameterized settings, it's really not appropriate. So if theory of optimization cannot be based on convexity, then what should it be based on? And actually, there is a beautiful condition by Polyak and Lysevich, PL condition, which probably many of you have seen. And it's from 1963. It simply says that it's a lower bound on the gradient, right? It says that the gradient is bounded by the value of the loss function minus the function at its minimum. And this is very nice because this is a first order condition. It guarantees convergence of gradient descent, and it's invariant under nice transformations of W. Well, basically, you don't want them to. You want to have some sort of nice Jacobian of the transformation, but it's not a very strong condition. The only problem with this is that it's kind of annoying because to show this condition, you have to know something about the minimizer, right? The value at the minimum value. But if you know the minimum value, right, it's a little bit of a chicken and an egg problem, because to know, you want to prove something about W star or L of W star, but how do you know this, right? Well, you don't know it until you have this condition. But there is actually a very simple fix, which we call the PL star, which is simply the following. You just remove this term. You just replace it 0. Okay? If you don't like something, just cross it out. That works beautifully. Turns out, of course, you need to assume that this is non-negative L of W for this to make sense. So turns out that this condition, first, it's point-wise defined, so you don't have to say that it's on a set. You just define at a point. Second, it actually now guarantees. So what do I mean by guarantees? You have to I'll discuss this in a second, but you have to have this condition hold in a ball of some radius. If it holds in a ball, then you can guarantee existence of solutions for the equation. So what do I mean by solutions? L of W equals 0. So that's my original system of equations, f of W equals y. That's one. It guarantees us convergence of gradient descent with a fixed step size. Actually, what is more surprising, it guarantees even convergence of stochastic gradient descent with a fixed step size, which is not really the case for standard convex. In some sense, it's stronger than convexity. I mean, in some sense, it's much weaker, right? Because it's a first order condition. It's just gradient. But in some sense, it's also it gives you something more, right? Because stochastic gradient descent with fixed learning rate converges. And finally, it's controlled by the tangent kernel, which I'll discuss in a moment. And that gives some sort of analytical control over the property of this system. OK, yeah, so. Oh, and by the way, please feel free to interrupt me at any point and ask questions. I am more than happy to answer. So now, what is the tangent kernel? So now, basically, the tangent kernel kind of allows to give some sort of more analytic way to prove this. What is tangent kernel? And somehow based on neural tangent kernel by Jacob et al., they call it neural tangent kernel. Well, of course, it's defined for any differentiable map. So it's really just, essentially, it's derivative, right? So what you take the derivative of this, which is m by n matrix, and you multiply derivative by the derivative transpose. So it's a matrix whose size is n by n, okay? And it's so if you think about a learning problem, n is the number of data points. Okay, so that's a matrix. It's a matrix-valued function, to be precise. And now you can prove very simple proposition that, square loss is mu PL star at W if with mu equals the smallest eigenvalue of the kernel, right? It's I put a proof because it's like one line. So this is nice because this gives exact control over this. So it's somehow almost all of it boils down to finding the minimum eigenvalues of the kernel. What we will need to control the minimum eigenvalue of a kernel over a ball, some radius of some like really constant radius. Radius is somehow like 1 over that. Okay. Now let me just point out to give a little bit of intuition of why this makes sense. Why are overparameterized? So what does this have to do with overparameterization? Why do we want m to be bigger than n? And think about what happens when m is bigger than n, right? When m is bigger than n, this is kind of a long matrix. And when I multiply this by that transpose, I get matrix which is m by m. So it's a short matrix. And it is clear that this m by n matrix is essentially well conditioned. The smallest eigenvalue is separated from 0 when somehow the rows of this matrix are somehow linearly independent. And of course, if this matrix is long, the rows, it's very easy for it to be linearly independent. Just think about like this to be, suppose this is like a single vector. If it's a single vector, then the kernel is just a norm squared. For the norm to be equal to 0, every entry of the thing has to be 0. And that's a very strong condition. So you basically never expect every entry of the thing, if you think of them as being somehow random, right? Every entry is not going to be equal to 0. So you essentially always get well conditioned. So somehow when the longer it is, the easier it is for it to be well conditioned. And the easier for the PL condition to be satisfied. And PL condition is good because it guarantees us a lot of things for convergence of gradient descent type methods, which we like. So that's basically the intuition that skinny matrices are well conditioned. And kind of an opposite to that is also true, and it's also like the theorem with maybe 3 lines to prove, is that you cannot have PL star unless the matrices, the system is overparameterized. And what do I mean by can? Well, you can, but if you wanted to have, if you want the system to be PL star independent of y for any y, then you have to have overparameterized system. It's easy to see that this must be true. So in some sense, it's kind of necessary and sufficient for well conditioning to be overparameterized. Okay, so these are pretty basic things, but they somehow have a lot of power. Okay, so now this is the theorem, which is essentially just reformulation of original theorem by Pollack. And a system of nonlinear equations, basically, which is well conditioned, meaning that it's bounded by some lambda mean, is in a ball of this radius has a solution in that ball. And so that's kind of what we want, right? And furthermore, you can say, again, this is some sort of variation of Pollack's result, but reformulate it a little bit in this kind of condition number way. that gradient descent converges exponentially with some sort of fixed step size. And the rate of convergence is controlled by this condition number. And this condition number is essentially like the condition number for the usual matrices, right? Except this is a Hessian, so it's not quite the same thing. But actually, if you put the square laws, it's very similar. And in any case, the lambda max is not a problem of this. What usually constitutes a problem is bounding lambda mean. And that's actually just lambda mean of the kernel. But for the classical theorem, for linear theorem, this is a constant. For this kind of nonlinear theory, you need to take inf of this. So you need a uniform bound on lambda mean. So this is very much like the classical theory for linear systems, except it's nonlinear, and actually quite general nonlinear. What you essentially, you just want over parameterization. OK, so that's now, here is a kind of an interesting thing, which really happens. I think this is maybe a little bit surprising, because this only happens for PL star condition and not true really for PL. And that's the fact that you can prove something essentially the same for stochastic gradient descent. But the only difference is that you need the ball to be bigger and you need the learning rate to be smaller. That's the way it works out. Actually, not completely clear why. So essentially, SGD converges with a fixed step size, converges the same way as it converges for GD, except with a smaller learning rate. And why is it not true? Well, to see that it's not true for standard gradient descent, just think about the loss function. X minus 1 squared plus x minus 2 squared, OK? If this is just this, you can kind of think of like this is like one data point. I don't know, in one dimension, right? If you do SGD here, this will try to converge to 1, but this will try to converge to 2, right? If you do SGD, you will, with a fixed learning rate, you will just oscillate between 1 and 2, and you will never converge. You can force convergence by somehow slowly decreasing your learning rate. That's a classical result. But that's, if you just want convergence, it doesn't work. But in this overparameterized case, it works because somehow it's like replacing this x by some other variable. And somehow they separate, and you get convergence because you get these different directions of convergence. So it's a really nice property of overparameterized systems. Non-classical somehow. So that's basically, so that's maybe kind of like the summary of this, is that well-conditioned nonlinear system behave like linear system under GD, and in fact under SGD if you take like linear overparameterized system, except that condition number are non-constant. So in some sense, overparameterized systems are remarkably well behaved, which is, somehow strange. I don't know. It's maybe from intuitively, it's a little strange. However, underparameterized system cannot be well conditioned in this sense at all, because if you take the tangent kernel, right, it's rank deficient. The rank of the tangent kernel is actually going to be mean of M and N. If it's underparameterized, it's always rank deficient, and it can lambda mean is going to be 0 always. So only for overparameterized system this applies. So that's maybe the kind of summary of this landscape. And let me maybe go over this picture, because it kind of gives you maybe some sort of intuition about what's going on. Yeah.
On this note that you just made, the Pollak's condition is kind of a worst case condition. You want that to be satisfied. The Pollak's condition, Pollak and is the every point condition. It needs to be said for every point. The gradient needs to be at least mu times the norm. Now the next point you made about these skinny random matrices is demonstration of this point for the random matrices. Right? Now, conceivably, that if the Pollak condition was true for typical points, it still would be fast converging, and maybe in that case you don't need to look at it. Maybe just a square by square or just not skinny matrices would still exhibit a good convergence.
That is possible. Well, so if it's not over-parameterized, it's not possible, right? Because lambda mean is going to be 0. So
yeah,
PL
but maybe
cannot.
marginally.
Just margin. Yeah. So it is true. So maybe this is too pessimistic. So what I'm saying is that as long, okay, I'm saying something a little bit weaker, right? I'm saying as long as it's sufficiently over-parameterized, it's very easy for PL condition to hold, and then we probably get convergence from kind of general hand waving. But actually, I'll very briefly note how to prove it actually for neural networks which are wide enough using this. But yeah, I think you're completely right. It may be that the condition needed is much weaker, like the true condition. So this is kind of the maybe the summary of this. This is this sort of domain, and all of W say here. And you can see that this is a singular set where lambda mean is equal to 0. And this set, well, it exists because lambda mean can be 0. But it's somehow a small submanifold. And there are points around the submanifold which are bad when things are poorly conditioned. And somehow points away from this domain are typical points somehow are well conditioned. And then as long as you have well conditioning in a ball, you have a solution set in this ball, and it's a manifold. So every ball in this kind of well-conditioned set intersects the solution manifold. So in some sense, it's like kind of like space-filling curve, and it fills space with something like radius of 1 over lambda mean. So that's maybe the sort of intuitive picture. So there are lots and lots of solutions here. And we don't know what happens around the singular points. I mean, there may be solutions here too, but we don't have a handle on how to prove that. So that's a summary of this. And maybe I'll just make a couple of points about how would you control conditioning, so go to something a little less hand-wavy in this sense. And you can kind of think of two ways to control this. And the first one is what you may call Hessian control. And you say that lambda mean at one point is like, say, 1. It's bounded from below. And then the Hessian is bounded from above. And it's significantly smaller. So suppose this is like 1, and this is, I don't know, like 1,000. Then you can say that roughly in a ball of a radius 1,000, this is controlled away from 0. Because this is essentially the derivative, right? And this is the second derivative. And the change of the derivative is bounded by the distance times the second derivative. So if you know this, that this is large and this is small, relatively, then you can control it in a ball, and that's good enough. So that's, and the second one is what maybe you can call composition control, is that if you compose two functions, and both functions are nice somehow, like this function has, lambda mean, which is bounded away from 0, and the second function has some sort of non-degenerate Jacobian. Then composition also has, because derivative, it's a first derivative, right, rather than the second derivative that you need for convexity, and derivatives multiply. So if a product of two non-degenerate matrices is non-degenerate somehow. So now, actually, interestingly enough, this too is what you need to prove that neural networks converge. Yeah.
I'm not sure how these arguments address the question of are you converging to the right thing, right? Because somehow this doesn't distinguish the case from I have a system of equations that's easy to solve versus a system of equations that's difficult to solve. Right? For some, writing the error, the sum of the errors, the minimizer will be the solution that I want. For some other ones,
yeah, it doesn't, right? That's why I'm saying that we actually have a decent grip on optimization. Generalization, not so much. Yeah. So it doesn't answer why this is a good solution, right? It just says that if I go to It just says that if you start somewhere here, you will find a solution in a ball of some radius around it, which is nice if you only care about optimization, right? But if you care about generalization, it's not completely satisfactory.
Well, even for optimization. Well, yeah, I guess in the optimization case, you could ask, is it the global minimum or something like that?
Yeah, so that we can show, right? This shows that this is a global minimum. So we can prove that there is a global minimum in this ball.
Well, it's not clear to me what are the assumptions in that case of the that guarantee that your condition on the minimum single value that you're going to fit.
So I need it to be well conditioned in this ball, and I can prove it by, for example, using Hessian control, which is the way it's done for neural network. So I need to prove that my lambda mean essentially is bounded from below in a ball. That guarantees that there is a global minimum. Okay. Yeah. But where they generalize this, I'm not saying anything about generalization at all, which is annoying, right? But yeah, sorry. So interestingly enough, if you have these two conditions, you can prove that neural networks actually converge, or wide enough neural network converge. And how do you do it? Actually, the point is this kind of constant NTK, which I want to discuss now, the constant of constant NTK transition to linearity phenomenon. So essentially, you can show that wide neural network have very small Hessian, but the lambda mean is somehow bounded from below, and that gives this one. And then you can kind of decompose them in a composition of two things. So notice that these are kind of a special tools, because my claim was much more wide. I kind of said that any over-parameterized model is good, but this is saying some pretty special condition about the Hessian. So there is some sort of disconnect, but it's good enough at least for neural networks. So 1 plus 2 imply convergence for neural networks, for wide neural networks, I should say. OK, so that's kind of Hessian control. Let me just skip this because I'm running out of time. Now, here is, I would like to very briefly discuss this constancy of NTK, because I think it's really an amazing recent finding, which was first identified in this paper by Jacob Gabriel Hogler, which I'm sure many have seen. They basically proved that, so what they showed is that, along in the optimization trajectory, this thing is just constant. And like, why should it's an amazing thing, right? Because why? For wide neural network, for very wide neural networks. And there were like other formulations, like it has linear dynamics gradient descent in the parameter space. So let me give a kind of a reformulation of it, which I think is easier to sort of understand. And notice, by the way, that constant NTK, it's not obvious that constant NTK actually is equivalent. So for a linear function, NTK is obviously constant because it's a derivative, right, of a linear function. It's a constant. But it's not obvious the other way around, because if you think about it, suppose your output is a single variable, right? If the gradient is constant, is it true that the function itself is constant, right? If norm of the gradient is constant, is it true that the function is constant? Yes, actually it's true, but I don't think it's obvious necessarily right away. You have to prove it. But in any case, it can be proved. So it's equivalent to linearity. And that's why we call it transition to linearity, because it's really what it means. It really means that the function becomes linear. And it becomes linear in some ball of a fixed radius. Actually, it's a little bigger than fixed, but in any case, we can just think of a fixed radius. And as the network becomes bigger, the function becomes more and more linear in that ball. And basically, the notion, what is the simplest way to think about it? If you have a function, right, you can write it as f of 0 plus d of f0, the derivative, plus second order term at some point inside. And this is Taylor series with a Lagrange remainder term. And notice this is exact. This is not an approximation. This is exact because this point is somewhere in the ball. So it's enough to show that this Hessian is small in a ball. And that turns out to be the kind of underlying thing. Notice this is actually not related to optimization as such. It's just a property of the network itself. which I think is kind of nice to separate optimization from the property of the network. So this is a theory. This is from our paper with Choi Liu and Li Bin Zhu. So for a class of neural networks, if they're of width m, the Hessian is bounding, and there is some log factors here, is by 1 over square root of m. And what it means, of course, that as m goes to infinity, as you take wider and wider network, the Hessian becomes smaller, but actually at 0 and at the value at 0 and the gradient of the function stay the same. Because, okay, I didn't exactly say how to scale it, but it's scaled the way that this is constant, O of 1. And this gives you the form of the neural network, and then this is 1 over square root of m. It is kind of not trivial, so maybe I don't want to go over this example, but this is a really simple example of this. I really like it because I think this actually shows what is happening here. And let me just point out that if you take a very simple 2-layer neural network with the first layer fixed, so the second layer fixed, the first layer is actually changeable. So you get this quite interesting thing. You have a Hessian, which is a diagonal matrix, and you have a gradient of, and the gradient is clearly of the order of 1. And you can see that because the Hessian is a diagonal matrix, its spectral norm is of the order of 1 over square root of m. But that's because it has a special form. It's not because of the interest. So if it were not a diagonal matrix, it would not be generally this. And you can kind of like write it a little bit more carefully, and then you realize that essentially gradient is of the order of some vector, of the 2 norm of a vector, and Hessian is of the order of some sort of infinity norm of a vector. Again, I'm sorry that I'm not explaining this. But, and somehow in dimension m, right, in high dimension, 2 norm is much bigger than infinity norm. That's basically what is happening. So it's a somewhat subtle phenomenon that happens with this transition to linearity. It's not something, I mean, it's not, it can be proved, of course, but it's like, why should it be true? Not so clear. And let me, maybe I will very briefly describe this very recent work with, you can actually take it more general for arbitrary directed acyclic graphs. So you can think of arbitrary neural network. And what is arbitrary neural network? Well, a neural network, a feed-forward neural network, is given by some graph, right? It's a DAG, directed acyclic graph. And so imagine I have something like this. And you can kind of think of like, OK, what are the layers here? Well, actually, the input would be the first layer. And then if there is only one step from the thing, that would be the second layer. And then if you can get to this in 2, then it would be the second layer, and so on. So that's how you layer this thing. And then it turns out that the correct actually definition of width for such thing is the minimum in degree for like 0 layer, input layer, of course, has like 0 in degree. And the first layer is the in degree of this is given by the number of inputs. So you don't control those things. But you can control everything else. So in minimum in degree outside of the zeros and first layer is the correct notion of the width. And what happens is that for a neural network corresponding to a DAG with minimum in degree m and linear output layer, the same thing holds. You have the Hessian corresponding to the thing, which is 1 over square root of m. Now, I am slightly hiding something here because we need some pretty weird condition that the sizes of the neural network cannot be like, they have to be like polynomially of each other, polynomially big. So it's not quite any graph. It's like graph whose layers are polynomially somehow comparable. But it's a lot of graphs. Like you're not allowed to have the first layer of degree m and second layer of like e to the m. Why? Actually, it's kind of weird because it seems that it boils down to some conjecture about random matrices. Maybe it's true, but no, it's not known how to prove it. In any case, OK, so yeah. Essentially not. We mean something like maybe twice differentiable. We need something like that. Yeah. So essentially any activation, any smooth activation. So yeah, you always get this. And somehow you can think of it as somehow assembly of neural networks, because you can prove that every pre-activation somehow iteratively are linear. And then you can kind of propagate this through the graph. And from that you get the Hessian to be small. Ankur, how much time do I have?
I'm going to probably end 5 minutes before, so you've got about a bit over 10 minutes.
Okay. Yeah, good. I want to discuss Catapult because I think it's very interesting. And although I don't have a lot to say about it, but I have something to say about it. And I can at least describe what it is. Okay, good. So that was kind of the first. So the first thing is that over-parameterized systems kind of in optimization look linear. Second is that this big neural network, quite general form really, almost arbitrary DAG, are actually linear when they're wide enough. But the third thing is kind of weird, because like the third thing is like, well, it's linear, but yet it's not linear. There is some deviation from linearity, and it's quite interesting. I think, and it was first identified in this paper by Lefkowitz, Bari, Diasol, Dickstein, and Gurari. Here is what happens. And it's, I don't think it's a perfectly reasonable deviation from linearity, actually, because it's kind of surprising, as you will see in a second. So imagine I have linear dynamics. So I hope, you know, you remember if I have like a linear system, right, and I'm solving it by gradient descent, I can solve it whenever my step size is smaller than something like 2 over lambda max, right? So my maximum step size is allowed to be if my system is something like, you know, if I'm solving ax minus y squared, if I can do some sort of gradient descent as long as my step size is smaller than the maximum 2 over maximum eigenvalue here. So that's a kind of critical value. So before this critical value, you have monotone convergence of your gradient descent. Above that critical value, you get monotone divergence. Well, monotone, yeah, it just diverges. But here is what happens with this catapult phase. So you have two values. You have this critical value, which is the same as before, but you have this some sort of other maximum value. And you have monotonic convergence here. You have, and this is the same as that one. You have non-monotonic convergence here. So your loss function first shoots up and then comes down. And you have divergence above this. So you have the three regimes. So for example, system which shows this, right, cannot be linear because it has some sort of extra phase. Now, if you think about what happens, I think this is kind of, this is from our paper, which we're planning to put on archive soon, with Libin, Chavelio, and Adid, Radha Krishnan. This is what happens here. So if you take a small step, so imagine this is a ball which I had before, right, in this kind of diagram. So in this ball, if you step with a small step size, you kind of converge to a solution, and you stay in this ball, and everything is nice in PL land and so on. And the kernel here actually doesn't change very much at all. Now, if you take a bigger step size, like double the step size, and you get into this catapult phase, you get a much, much longer trajectory. And the interesting thing here is that the kernel changes, it actually decreases. The norm of the kernel decreases. The loss function kind of shoots up and then goes down. And you still converge to a solution, but the trajectory is much longer. So here you see the loss function goes down monotonically, and the kernel stays, because that's this kind of NTK type of regime. And the interesting thing is that even here, the whole trajectory is still in the NTK regime, meaning that, what do I mean by NTK regime? It means that the Hessian is actually small across this whole trajectory. And if you decrease the step size here, you still converge here very quickly. So, yeah.
I say that this is not consistent with linearity. I mean, a linear system can perfectly do this kind of things. I mean, it just perhaps not normality.
But how would a linear system, I mean, linear system would diverge, right, if you exceed the maximum eigenvalue?
I mean, it's not about eigenvalue, so that's in the values. So that kind of behavior is typically non-normality.
Not what?
Non-normality. When you have a non-normal matrix, it doesn't commute in the out, you get it, I mean, like in turbulence, where you have exactly the same kind of things.
So when would it be, I mean, it cannot be a system of this form, right? Because this, I'm
I don't know exactly what is it that what dynamics you actually do.
let's say you're doing gradient descent for something like this. How would you get that behavior, right? You cannot.
If you're only doing that,
I don't think you can get that.
You cannot, right? Because for this one,
your Hessian's going to be PSD in this case. So I think it's not so obvious, right? But it definitely could still be linear, just not that particular type of linear.
But you can set similar effects with, I don't know probably with the analysis of discrete dynamical system based on the pseudo spectrum, then you see something like transition effects.
Yeah, exactly.
But as Pablo said, that similar effects could be visible with linear dynamics as well.
so what do you mean by linear dynamics in this sense?
Non-normal matrices, you've got like some of the eigenvalues are really small, and then with transition effects, yeah. Yeah, in other words, the pseudo-spectrum of a matrix would describe this type of effect. I believe it's more complex than that, but the question is, could you explain that with pseudo-spectrum?
Maybe we can discuss it, because I don't know, but maybe we can discuss it, because I would like to understand how that works. Well, one thing you can see here is that actually the norm of the kernel decreases along the trajectory, which is, I think you cannot have it. But yeah.
that would still be consistent with linearity.
Can you get the norm of the kernel decreasing from that system? That would be very interesting.
It's a linear model that kernel cannot.
It's somehow fixed,
Yeah,
but maybe with this, I don't know.
Let's take it.
Okay, maybe we'll take, yeah, but in any case, it's definitely not a model of this form. Yeah, that's, okay, but yeah, so that's kind of, so let me point out something quite interesting here, which I think is kind of shocking, which actually they observed in their paper, so this is not new. Here is what happens. So if m goes to infinity, the network's transition to linearity, right? It becomes more and more linear. And you would think that as it becomes more linear, it becomes really of this form, right? And I think we agree that at least this system cannot show that behavior. But what is happening is that even as network goes to infinity size, and as this thing becomes more and more linear, this thing doesn't shrink. This regime stays. And you always have this kind of catapult behavior with large eigenvalues, and you always have this convergence. And what is happening, of course, is that because it's more linear, the thing is closer to constant. And so the trajectory with catapult becomes larger and larger. So as you tend to linearity, there is this regime which becomes somehow longer and longer. It becomes more and more nonlinear, or more and more weird in some sense. And so this loss also increases, right, when you transition to linearity. So in that sense, it's kind of a non-perturbative phenomenon, because even like though the actual system is very close to linear, that small deviation from linearity gives you some sort of non-continuous effect. You have this very long trajectory of it. So yeah, I mean, we have some analysis of this and for quadratic functions, so we can show that something like that can happen for specific cases. I mean, it does look like it happens for a lot of neural networks, and maybe all of them. And I don't know, like somehow the analysis and what we can show doesn't really, what we can show is much, much more narrow than what happens to having practice. And let me point out one more thing. It does look actually that, and I'll stop here maybe at this slide. It does look like Catapult Dynamics in practice can in fact improve performance in generalization, which is kind of slightly shocking. And that actually on like a bunch of experiments. I'm showing one, but it is true. So this is the loss. And it looks like if you take as big a step size, you actually get this catapult dynamics and you get this better performance. Like why? I don't know. So maybe let me just summarize. I'll skip that one. So I think this is sort of the summary. Over-parameterized systems behave like linear functions. You have this transition to linearity, but it looks like there are some very interesting nonlinear effect, which may be even important for generalization, like for unclear reasons. But it appears that maybe that's something that we need to understand if we really want to have the full picture. Although I guess it remains an open question whether it's important or not. And I'll stop here. And thank you.
We have time for a few more questions. We can pass around the microphone. So I guess we had a lot of questions during the talk, but let me add one more. So one of the things I'm curious about is, so the first part of your talk was about situations where we can analyze gradient descent with non-convex loss functions. And of course, there's situations where it tells us some properties of the architecture where we can analyze it. But it's not so clear that those are aligned with properties of the architecture that behave better in practice with generalization. So can you say more? I mean, do we really want the systems to have architectures so that they're approximated by linear functions? Maybe you can compare it to some of the feature learning regimes. What does this teach us from a practical standpoint about how to pose the question or about what to do?
Yeah. I think, we have seen that people in practice use bigger and bigger architecture, and that has been very consistent over the last maybe 10 years. Now, of course, the width has to be measured relative to the data, right? So the size of the data has also grown. So are they over-parameterized on the data that we have? It's unclear. But I think what is true is that you use one of these big systems on a much smaller data, you still get very good performance. And you can say that, yeah, that is probably pretty close to linear. So at the very least, you can say that linear systems can have very good performance. Now, are they like this, for example, feature learning regime, are they important? I haven't seen a sort of very convincing argument that they're like really important. But on the other hand, like as I just shown, right, this catapult regime, which is some sort of weird nonlinear regime, does seem to have some benefit for generalization, at least on some limited set of experiments. So it's very, it's not unthinkable that something like that happens. But I guess I'm kind of hedging my bets here. Yeah, it's an open question, right? But I think we can go quite far with linear. Maybe that's.
Misha again, and we'll take further discussion.
Thank you.